Hello and happy Thursday. So today we are looking at potential difference and electromotive force. We're also looking at electron guns, which I'm afraid have a more exciting name than they actually are. But either way, that is what we're looking at. So if you can please title and date, make sure you are writing the correct date. As you know, it's not the 8th of January 2020. Good news, we've already done 2020. We're on the up. 2021, here we go. Okay, so first thing is potential difference, also called voltage, is the energy transferred per unit charge by the electrons or charge carriers. So as you know, electrons are given energy by a cell or battery or whatever is providing the energy, and they carry it around the circuit to a component, a bulb, a resistor, an LDR, and they give that energy out. So that energy per coulomb of charge is called potential difference, and it is measured in volts. So I am lazy, you may see me refer to potential difference as PD. That is fine if you do the same. 1 volt is 1 joule of energy transferred per, in fact, let's say, I'm changing that, apologies. Per coulomb. Now the reason I've changed that is because actually I want to draw your attention to the definition of a volt has to contain the units that it relies on. So what I mean by that is if I ask for potential difference, it is energy per charge. They are all quantities, they are not units. If I ask for the definition of a volt, I want joules per coulomb. And can you see the difference there? The idea that if I define a unit, I need to use units to define it. If I'm defining a quantity, I use quantities to define it. And the reason that I'm making such a song and dance about this is that they quite like exam questions based on this. So it's a really simple thing that people muck up on. Just pay attention as to whether you are defining a quantity or defining a unit. Anyway, enough of that. Let's look at the equation underneath. So this is an equation that pops up in, 4-5 different modules. If you are not sure about something and it vaguely contains anything to do with energy, chances are it's this equation, or electricity, should I say. So potential difference, V, is equal to the energy transferred, W, divided by the charge. And that genuinely, it pops up in so many different places. So learn that one by heart. I know you're given them all on your equation sheet, but really useful if you always have that one to hand. So, write those down and then let's move on to the next bit. So, next bit is voltmeters. A voltmeter should always be connected in parallel to the components. It should have an infinite resistance so that no current flows through the voltmeter. Now, a reminder that the idea of a voltmeter is that it looks at the energy per unit charge on either side of a component. So potential difference, it's kind of in the name, is the difference in potential energy at 2 different points. Hence why a voltmeter must attach itself to 2 different points of the circuit. In younger years, I quite often refer to a voltmeter like the M&M song, which, I'm going to do it, but don't judge me for it. It has to go round the outside, etc. Please don't write that in the exam. That's the only fault with my wonderful teaching method of using M&M, is that in exams, students quite often write, it goes round the outside. It does not, it goes in parallel, and it is quite key, but it's a good way of remembering it, so, that's why I use it. So yes, pause, note, etc., and then let us move on. In a circuit, the cell does work on the charge carriers, i.e. gives them energy. So that's the language I want you to use when describing energy in a circuit. The cell does work on the charge carriers. The resistor, or bulb or thermistor, the component effectively, has work done on it by the charge carriers, i.e. it takes the energy from them. So given energy in the cell, energy taken away in the component. Work done on in the cell, work done by in the component. Hopefully that's fairly straightforward. So now I'm going to introduce a new definition, a new name, and that is electromotive force. And you can see here it's shown by this curly E. Okay, and it should always be shown by a curly E. It should not be shown by a straight E, and that is because it's actually a Greek letter there. So off the top of my head, I want to say it's epsilon. So it's a capital epsilon. The amount of energy per unit charge put into the circuit is called the electromotive force. The amount of energy per unit charge taken out of the circuit is called potential difference. So hopefully you can see the difference there. You've got energy being put in, electromotive force, or should I say work done on the charge carriers, electromotive force, work done by the charge carriers, potential difference. Okay, there are some summary questions on page 138, which we will go through later on Zoom. So don't worry about them now, but they are on the topics that we've just been looking at. Okay, the next bit we are going to go on to is the electron gun. Now, the electron gun is basically how we get a beam of electrons, and they're very useful for doing various experiments. And it looks like this horrible diagram here. So let's just break this diagram down. You have a hot cathode. Now, just a reminder that a cathode is negative. Oh, I should really make this smaller. Hang on. Let's try that again. Something bad. Smaller. Okay, so negative. So the hot cathode is negative. That means there are an excess of electrons. So you see it's hot as well, it's heated red. When things get hot, they do what is called, you don't need to make notes on this bit, by the way, I will give you proper notes, thermionic emission. Now, breaking down that word, therm, no real surprise, is temperature. So when things get hot, they do thermionic emission. Ionic means that they give off their electrons, creating ions. So thermionic emission basically means if you make something negative and heat it up, it's going to give off a load of electrons. Perfect. Then, on the right-hand side, you have an anode, which if you remember is positive. So the electrons are going to be attracted to it. So they get attracted towards it. And can you see the hole in the middle of the anode there? Some of the electrons are able to go through the hole and come out. And what you end up with is this lovely accelerated electron beam coming out. Now, just a quick note, you can see it's evacuated, which means basically it's a vacuum. There is no gas or air or whatever in it, so that the electrons do not interfere with anything. They're just able to go through, and that's it. So you are going to have to make notes on how this actually works. So let's just go down here. I've basically explained what I talked about. Metal filament heated by electric current. The electrons inside gain kinetic energy. Some electrons gain enough kinetic energy to escape the surface of the metal. This is called thermionic emission, as discussed. The electron gun is in a vacuum and the anode is given a high positive charge. This means the electrons are attracted to the anode and accelerate, gaining more kinetic energy. If the anode has a hole in it, then the electrons can travel through, producing a beam of electrons with a specific kinetic energy, controlled by the potential difference between the filament and the anode. So the idea is, if I make this 10 volts, and it's minus 10 volts, then fabulous, the electrons will accelerate a certain amount. But if I make this 110 volts and this minus 110 volts, you can see they're going to accelerate a lot more and have a higher kinetic energy. So if you can please write down the steps. It might be easiest if you screenshot that diagram, if I'm honest. I don't need you to try and draw it. That would be rather mean. So yeah, screenshot it. If you want to try and draw it, fabulous. But sorry, it is a bit of a pain. Normally I'd obviously print it out for you. So the final bit you're going to do is energy transfers. As the electrons accelerate towards the anode, they gain kinetic energy. The work done on the electron is equal to EV. Now this comes from the equation we literally just looked at, which is W equals QV. We did it as V is W over Q, but it's the same equation, where W is the work done, Q is the charge, and V is potential difference. Well, here the charge is the charge on the electron, so that's 1.6 times 10 to the minus 19 coulombs. V, as we said, is potential difference of the field, so that's measured in volts, and W, as we say, is work done on the electron. Then all that work that is done by the electric field to speed up the electron is turned into kinetic energy. And so I can make it into half mv squared. Now please notice there are two V's here. One of them is a capital showing potential difference. One of them is a lowercase showing speed or velocity, which is measured in meters per second. Mass of electron can be found on your equation sheet, but from memory it's 9.1 times 10 to the minus 31 kilograms. You will want to check that one because as I say, have done that from memory. So that is all your notes. You then have two sets of questions that we're going to go onto Zoom and work through. That is page 138 and page 140. So if you can please, whenever you're finished these notes, come join me on Zoom and we shall sit and work through them together. All right, thanks everyone. See you on